Literally, I was like, I'm gonna make this the rest of my life.
Okay, so for the last segment of this, where we'll end off today is we saw in the last, we saw in that last spectrum that we can determine the structure with the coupling. And the problem is that there's limitations to when you're going to see nice, clean splitting patterns. So basically, when you're looking at a spectrum, if you see a singlet, a doublet, a triplet, or a quartet, that means that you're a hydrogen with only one group to your side, one neighboring group, and it's either has a CH2, CH2, CH3. If you're a hydrogen, if you don't have a hydrogen on carbon, you're not going to see it. And if you only have one neighbor, you're going to see 2, 3, and 4. When you get into these complicated structures, that means you're a group in between two non-equivalent groups. That's what that means. Sometimes they'll be perfectly symmetric. Other times they'll be kind of unsymmetric, which might mean that you have two groups really close in chemical shift that are overlapping. And you'll see some examples of that, particularly in the homework. So the limitation on all of this is the following: that when you have two chemical shifts, so if I have two sets of hydrogens, there is a distance between those two hydrogens, between the center of the peaks, that's the difference in chemical shift. Okay? And that chemical shift can be measured in Hertz. We said it was unitless before. It really is a number of Hertz. So you have your center of your peaks, and then off to the side, you have like your split peaks. When the distance between the sets of peaks, which would be your distance in chemical shift in Hertz, when that becomes small, so that now the peaks, the sort of coupling peaks, are now kind of overlapping, you don't end up with nice patterns anymore. So when peaks are really close together, so that their chemical shift difference in Hertz is starting to be about the same as the distance between the peaks in Hertz, the coupling constant, all the math falls apart. And you don't see nice triplets and doublets and quartets anymore. So here I can simulate this, because my little Mac program had the ability to take that same isobutane or isopentane that we just worked with, and this is what that would look like at 60 megahertz, which would have been one of the original NMRs. That's what that would have looked like. I can't make heads or tails of that, because what happens is all of the peaks are now so close together that the distance between them in Hertz is about the same as the coupling constant, and this is what's called a second order spectrum, which I can't interpret. So what do? I want to spread the peaks apart in Hertz. The coupling constant is constant. So you can't change the coupling constant. It's constant. Right? If we were to have a quiz next week, I would say, which one of these things can you change by going to a higher magnetic field? And one of them would be the coupling constant, which you cannot change because it's constant. But you can change the distance between the peaks in hertz by going to a higher magnetic field. So what we do is we jack it up to a 360 megahertz instrument, and now all of a sudden the peaks are separated, so now they become nice symmetrical patterns. So now I've increased their distance. So if you think about, why does Case need a 900 megahertz instrument? Well, they're a private school, they can do what they want, right? They got their own money. Why would Ohio State need a 900 megahertz instrument? Well, because it's Ohio State. It's going to get what it wants too. And there's not going to be any football funds going to pay for that. But why do we need these big magnetic instruments? Why do we need 900 megahertz? Well, I want to do biomolecules. And so think of all the hundreds and thousands of protons that are going to be in biomolecules. And if they're all smushed together, I'm not going to get normal triplets and quartets and stuff. Plus, I'm not going to see them because they're a big jumbled mess. But if I go to a 900 megahertz spectrum, now all of a sudden I can begin to separate them out. And I can see them and I can make sense of them. So whenever you're doing biomolecules, most of the time you need a minimum of 600 all the way up to 900, or I'm sure somewhere in the US there's a 1, whatever the next would be, terahertz or something, that there's a magnet that big, and a building even bigger to fit it in. And somebody had to pay like $20 million for that, or maybe even 30. Usually when you go from 300 to 600, you double the price. When you go from 600 to 900, you double the price again. So if we wanted to do a lot of biomolecules here, I should have bought the 600 from the guy in Case. But I don't have 32K, and I don't have a room to put it in. And you can't have two big magnets in the same room. That doesn't end well. So that's okay. Case has big magnets. We can make friends, and we can go down there and we can run samples. Or we got Akron, or we have Kent, or we might have friends at the Ohio State University. You never know. So we can go out and use these bigger magnets. No school ever purchases just for their own use. They always have a consortium. But that's why we want to use big magnets, because we want to do biomolecules or polymers, plastics and other things. We want to spread these peaks out. So this is the best example. This would have been what I had to learn, which I like to think is why I got a C in spectroscopy in my undergraduate career. Then I just went and did graduate work in it and still do it. So doesn't mean C's don't necessarily, they're not going to kill you for life. Unless you're going to medical school, I guess. But, I got to see in this stuff and I'm teaching it. What does that say? But I like to blame the fact that I couldn't make heads or tails of their NMRs because they're all squished together. It's worked for the last 30 years. It's been my way of excusing that. So that's why we go to higher fields. The last thing we got to deal with protons is we have to deal with OHs. We have to deal with OHs, NHs, and C double bond OOHs. They don't show up in our NMR spectrum. I know I've shown you some NMR spectra that where they're there. They're really not. Those are computer-generated spectra. If I try and take a spectrum of an alcohol, I'm not going to see the OH. So I have to explain why. In order for me to explain why, I have to tell you how we measure the NMR spectrum. And we take a tube that's 5 millimeters wide, so that's wider than a melting point capillary. I put a solvent into it, and I put my sample into it. My solvent cannot contain hydrogens, because my solvent peak would be huge, while my sample peak would be little, and I'd never see anything. So in the old days, we used to use carbon tetrachloride, CCl4. No hydrogens, no problem. A little carcinogenic, very heavy, doesn't dissolve everything, and doesn't work with our newer instruments. So instead what we do is we take a solvent and we replace all the hydrogens with deuterium. Right? Deuterium from lecture. The first time you see a D in your organic book, you go, wait, there's no D on the periodic table. What element is that? And it's not. It's the isotope of hydrogen with a mass of 2. And so you can basically enrich your molecule in deuterium. Now, the thing you have to know about these isotopes is every isotope has a different Larmor frequency or different spinning frequency. So for instance, my hydrogens are spinning at 300 next door. My deuteriums are only spinning at 40, 30 to 40, because they're a different isotope. My magnet is the radio, and my console is the radio station. So if my radio station is sending out, how long is that analogy going to work for, right? Radio stations. The ones in the car, the one you have in your car that's not attached to the internet, that radio. The radio station sends out 300 megahertz. If the magnet's turned to 300 megahertz, it sees protons. But it's not tuned to the 40 of the deuterium, so it wouldn't see deuterium. So all the deuterium doesn't show up as a peak. If I want it as a peak, I got to tune the magnet down to 40 megahertz, then I'll see deuterium. So we use solvents like D2O, CdCl3. Basically take any solvent, methylene chloride, CD2, CD2Cl2, dichloromethane. We can take any of those solvents as long as we can replace the hydrogens with deuterium. We've got an NMR solvent. CdCl3 is the cheapest, along with D2O, and then they get progressively more expensive after that. There's a collection of them next door because I've got them all. Now, so the D doesn't show up in the proton NMR spectrum. What happens when you have an alcohol? What happens when you have an alcohol in solution is that the OH is hydrogen bonded to another OH. These molecules are constantly forming hydrogen bonds and then they're breaking apart. Well, and the same thing would be true for molecules with NHs, and the same thing would be true for the carboxylic acids. They're going to be constantly hydrogen bonding with other molecules. Well, when the alcohols hydrogen bond and they break apart, does the hydrogen always stay with the same alcohol molecule? No, they can be kind of swapped back and forth, or a better word is exchanged. So now we're back to my camera. How quickly do I take an NMR spectrum? Not that quickly. So over the course of my NMR experiment, I see OHs attached to all sorts of different OH groups. And what happens is, instead of them being single peaks, which they would be if they were stuck to the same O for the entire experiment, when they start exchanging, the peak begins to broaden out. And sometimes will broaden out so much that it just disappears. So a lot of times we don't see OH or NH or carboxylic acids in the spectrum because they're exchanging very rapidly. And when you do see a peak and you say, well, maybe that is an OH, what you do is you add a drop of D2O to the sample. Now all of a sudden the deuteriums are swapping with the hydrogens and the hydrogen peak disappears. Same thing would be true for an NH or a carboxylic acid. So if you think you're seeing those OH, NH's peaks, you add V2O to them, and they disappear. And that's a classic way to determine whether or not the peak is the OH. And how do you remember if it's an OH, NH, or carboxylic acid? My suggestion would be those are the hydrogens that get removed by like Grignard reagents, right? Those are the ones that you got to avoid when you're making the Grignard. So now if you just say I've got to avoid them, and they're the ones that I can't see in an NMR, you've doubled your memory capacity. You only have to remember one fact and two. We don't want to overload our brains with unnecessary organic chemistry. So that's what happens with OHs. So I don't even count them. And I don't assume that I'm going to see them. That means if you're a hydrogen with a neighbor as an OH, that OH isn't there long enough to split you because it's constantly going, it's constantly exchanging. So is that it? Yeah, that's it. So now we're ready to do some analysis. So here is a C4H9Br molecule. It's a butane. And so how many different butanes do we have? Possible. There's one N-butane. Or sorry, N-butyl bromide. Or just butyl bromide. The N's redundant. Right? 1, 2, 3, 4. What else do we have? We have an isobutyl bromide. We have a tertiary bromide. And we've got a sec-butyl bromide, right? So we have 4 different bromides of butane that are possible. And I think we have 1, 2, 3 spectra. So one got left out. So the question is, can we match the spectra, each spectra to the right molecule? And there's a lot of ways to do this. For instance, if for each one of those molecules, how many sets of hydrogens do you expect? How about for the N-butane? How many sets of hydrogens, how many sets of non-equivalent hydrogens do we have? Because that'll tell us how many sets of peaks we should see. So for butyl bromide, what do we have? How many? Give me a number. How many? 2? Give me another number. How many unique sets would we have for butyl bromide? Or I don't care. Give me a structure, give me a number. How many for tertiary? Yes, less than the other ones. What number? 1. So the tertiary bromide should be a single peak. That's what you're saying. That's not what you're saying? Butyl bromide should have 2 peaks. I would have stuck with the 1. I got 3 CH3s. Are all 3 CH3s equivalent to each other? Yes? No? I know you're trying to wear me out, but you're not going to. We're going to have to finish this. So if you're just thinking, well, if we can wait them out, trust me, I would love to end right now. Right? So then I can go back to my office and do fun things like phone interviews for an administrative assistant, and, you know, that kind of stuff. But we got to finish this. So we got to suck it up. So are all 3 CH3s the same?
No.
Yes, they are. I like the confident answer, but
I just want to move on.
so why all 3 of them are the same? Because if I let's say I replace the hydrogen with a bromine, I would end up with a 1,2 dibromo. So all 3 CHs are the same. They're all equivalent. And how many neighbors does each CH3 have? 4. How many neighboring hydrogens does each CH3 have? Neighbors. Adjacent. How many? 0. There are 0 adjacent hydrogens, which is true because the carbon they're attached to is a quaternary carbon. There's no hydrogens. So with all CH3s being equivalent and no neighbors, that means the spectrum should be a single peak. So this is the spectrum of tertiary bromide. So someone was correct that yes, that will have the lowest number of peaks. With 1, that's the least you can have. So there's spectrum 1 of, so we can take that one away because now that one's been assigned. How about sets of hydrogens in the remaining 3 molecules? Somebody want to give me a molecule and a number?
For the sec bromo.
For the sec butyl bromide?
Sec butyl bromide. 4 peaks.
4 sets?
Yeah, 4 sets.
4 sets, we agree with that? Yes, no? What?
I think 3.
He's right, 4. There's 4. Because the 2 CH3s are not equivalent. So there's 4. How about for the butyl bromide? For the N-butyl bromide? You got a CH2, another CH2, a CH2, and another and a CH3. How many? Give me a number. What's your number? 3? Give me another number. Give me another one. 4. Now, how about for the isobutyl? For the isobutyl bromide. What I hear?
2.
No, 3.
No.
It's 3. It's 3. Isopropyl would be 2 cents. So, one of the ways that you can match the spectra up is to look at the number of groups of hydrogens that you should see. So with T-butyl, there should be 1. We've already made that assignment. So here we've got 4. Here we've got 4. We can eliminate isobutyl. Isobutyl bromide as a potential structure. So now we've got 2 that have 4 sets of hydrogens. Okay, so what am I going to do next? Because I need to assign the spectrum to the group. So how do you want to approach that? We could do patterns, right? We could do patterns, great. So give me the butyl. So for the butyl bromide up here, for the CH, and if you have to, just like in lecture, if you have to write out the complete structure, so that, for this one I'm looking at CH3, CH2, 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 and then a BR. So for that one, what would we pick the first? What would be the methyl group, the number of peaks, the coupling pattern for the methyl? Is it going to be a singlet, doublet, triplet, quartet, or more than 4, which I call a multiplex? What's the CH3 going to be? What'd you say? 3. I heard a 3. Somebody mouthed something. What did you mouth? Triplet. You can be more aggressive. Triplet. So that one's going to be a triplet. How about this CH2? Singlet, doublet, triplet, or multiplet? Multiplet. Okay. How about this CH2? No. How about the CH2 that's in between the CH2 and the other CH2? Is it in between 2 different groups? Sure it is. Because it's in between 2 CH2 groups, and now I got to go back. This is like chirality. Because it's in between a CH2 that's attached to a CH3 and another CH2 that's attached to a bromine, so those 2 groups are not the same. So what's it going to be? Well, it's going to be a triplet of triplets, right? Because it's a triplet on one side, triplet on the other, so it's going to be a multiplet. How about the CH2 attached to the bromine? No. No. All right, so we've eliminated multiplet and doublet on this side. Triplet. It's a triplet. How many neighbors does it have? It's got a CH2 as a neighbor. It's got a 3. So is there a spectrum with a triplet, multiplet, multiplet, triplet? Yes? Where is it? It's the next one. So triplet, multiplet, multiplet, triplet. Triplet, multiplet, multiplet, triplet. Great. So we know that this one is this. Okay, so you've matched the spectrum with the structure, but that's not good enough. Now I need you to tell me which set of peaks corresponds to which hydrogens in that molecule. So we've got peak 1, 2, 3, and 4. So match the number to the left. I'll take any combination you want to give me.
I think the biggest triplet is.
So peak number 4, that triplet corresponds to what?
Yeah, I think it's
D? So 4 is D. We like that? 1 is A. 2. B. 3. C. So, how do you get that? How'd you get D was 4? Whoever suggested that. Did you suggest that? I What? The 4D?
Because it was the biggest peak and the most hydrogens around D.
Okay, and integration-wise, if I look at these things, these integration markers, it's like 3+, so it would be the biggest peak. Most integrals. I can explain the A, B, C, D order with one thing. Brendan, do you want to do that?
Is it bromine?
Okay, the bromine. So what is the bromine doing to the hydrogens on carbon A? It's de-shielding them, right? That was weeks ago we talked about, well, a couple hours ago, we talked about de-shielding. Seems like weeks. So the bromine is de-shielding the hydrogens attached to carbon A the most. And so notice that they show up about 3 on your scale. That's where hydrogens attached to carbons attached to halogens will show up. And then I can go right down the line and go A, B, C, and D, because with a straight chain alkyl halide, the farther away you get from the bromine, the farther to the right you go. And what's the last peak on the right? A, CH. The last peak on the right's the CH3, and at least a couple times CH3s tend to be the last peaks on the right. Because they tend to be farther away from all of the other electronegative elements. As far as coupling patterns go, triplet, multiplet, multiplet, triplet. So let's just say, for the sake of argument, that These are just butyls we're doing. We could do pentals, we could do hexyls, all the possible hexyls. We could do all the possible heptals. Now don't shake your head because there's some up here. Right? So we can do these different ones. And I guess part of what I'm showing you is we couldn't tell the difference between methyl and ethyl before with any spectroscopy technique, right? IR, everything was an alcohol. But now I can tell the difference between an N-butyl and a tertiary-butyl and an isobutyl, if it was there, and a sec-butyl. But triplet, why is this a triplet? Well, first of all, why is it here? Because it's attached to a carbon, hydrogen attached to a carbon, attached to an electronegative element. What electronegative element? Well, in this case, I know it's a Br. The other one's a multiplet, so it's in between. The third one's a multiplet, it's in between. But they're getting farther and farther away from the bromine. The other thing you could do is you could count up the number of blocks and say this is like 2 1/4 blocks for A, probably 2 blocks for B, probably 2 blocks for C, and 3 blocks for D. Now, the 2, the 2, the 2, and the 3, if I divided everything by 2, I get 1, 1, 1, 1.5. Multiply them back by 2, 2, 2, 2, 3, corresponds to CH2, CH2, CH2. So you can use the integrations that way. So then we go back to this one. There's 4 peaks. What does it have to match up with? It's got to match up with the sec-butyl, right? So if I'm looking at the sec-butyl, here's what I'm going to do. First of all, I see a peak at 3. This is the hydrogen attached to the carbon attached to the bromine. So what kind of group is attached to the bromine? First thing, how about the integration? I can figure out what group that is from the integration. And that's what? A block. What's the middle one? 2 blocks, 3 blocks, and 3 blocks. So 2, and probably 2, 2, 3, 3 in terms of blocks. So divide through by 2 and go back to 1, 1, 1.5, 1.5, multiply by 2, 2, 2, 3, 3. So this is a CH2 group. That's a CH2 group. Except it's not. Then I've got 2 CH3 groups. Actually, this one at 2 blocks is a CH2. This one at 1 block, the one on the left, is a CH. So they're roughly 1 block per hydrogen. So I got a CH, I got a CH2, I got 2 CH3s. Well, right there, I have my puzzle pieces. I got a bromine, a CH, a CH2, and a CH3. How do I put them together? Well, 2 CH3s. How do I put them together? What's going to tell me that? The splitting patterns. So this CH is what? 5 peaks. That means it's in between 2 non-equivalent groups. The CH2 is a multiplet. It's in between 2 non-equivalent groups. The CH3, that's a doublet, is next to the CH. It's a doublet. It's next to the CH. The other methyl group is a triplet. It's next to the CH2. Okay? So the whole idea here is that the coupling patterns are not telling. We started that. Because I'm going to go back to the fundamental 3. The fundamental 3 things that we have to do with the spectrum. Number 1, chemical shift tells me that this is attached to the bromine. It tells me for those peaks, the farther to the right, the farther away I am from the bromine. The integration tells me the group. CH, CH2, CH3, CH3. And then, how do I put those pieces together? This is a multiplet, it's in between two groups. The next one's a multiplet, it's in between two groups. The first methyl group is a doublet, it's attached to the CH. What CH? This one. The CH3 at the end is the triplet. What's it next to? The CH2. So if you use all three fundamental things, you can put the structure together. And you can match up the spectrum. But it's not good enough just to match up the spectrum. It's good enough, what you've got to do is you've got to not only be able to, if I give you compounds, match them up with the spectrum, but you then got to tell me what peak corresponds to what peak, what set of hydrogens in that spectrum. So, one more time. A, B, C, D. For that sec-butyl bond. So that puts together our integration. It puts together our splitting patterns, but more importantly, it puts together also our chemical shifts. So that's where we're at. Everybody with me?
I don't quite understand the math for the integrations, like how you know to divide and multiply by those certain numbers.
So, well, I'm just ballparking it. So this would be one block. This is going to be like 2 blocks, right? And this one's going to be like 2 blocks here plus a half a block plus another half a block. That's like 3. And then this one goes from here to here. So that's like 1, 2, 3 blocks. If I really wanted to be precise, I would get a ruler out and I would measure that. I would measure the distance between this part of the plateau and that part of the plateau.
So what were you doing when you were saying like I'll multiply that by 2 and then divide that by 3? Like what was that? Oh, okay.
It's been 3 hours. I'm just as tired as you guys are.
Okay.
What I was doing was, here's what I was doing. So this is 2 blocks. This one's 2 blocks, right? This one is 1, 2. That's roughly 2 blocks. And then this was 3 blocks.
And that's proportional to the proton.
Well, so what you do is you divide by the smallest number.
Okay.
So when I divide those by the smallest number, I end up with 1, 1, 1, and 1.5. Since I can't end up with a fraction of 1.5, I have to multiply that to give me a whole number, which means I multiply back by 2 to give me a 2, 2, 2, and 3. So what that means is this is a CH2 group, the second one's a CH2 group, the third one's a CH2 group, and the fourth one's a CH3 group.
Okay.
So then this CH2 group right here is a triplet, which means it's next to another CH2 group. The middle one is a multiplet, so it's in between. The third one's in between, because it's a multiplet. And the fourth one is a triplet next to a CH2. So that's how I'm putting the structures together. So that's what we need to be able to do. So I could hand out some practice problems. And these are just these are butyls. This is, there's an isopropyl. There's a, these are propyls and butyls. Abort. So these are truly practice problems. Propyls and butyls. So you can take one of those. Normally we might sit here and do that, but at this point, I've been doing this a long time and I know that's going to be counterproductive for both of us. This one, though, is a little more challenging because this is the pentals. So these are the pentals. And now this one is going to be the homework assignment for next week. Okay? So what it says is that you have pentals, and each position on the molecule has a letter, and then there's 7 spectra, and each spectrum has a number. So you're going to match the number up with the letters. And it says, it originally said on Blackboard, now it says Canvas. So I guess what I'm going to do is set up a Canvas quiz that has numbers 1 through 27 or whatever, and then you're going to type in the letters that corresponds to that, and then it'll grade it automatically. Although I could just I have graders, and they need hours. So why don't we skip the Canvas part, and you can just put the numbers with the letters, and then they'll sort it out. Try and be neat, though, because they just might get feisty and just give you no points because they can't read. And I might support them in that. So forget about the Canvas stuff. So you take one of those, you can practice. This just was matching up the spectra to the spectrum to the compound. But I want more than that. I want the actual individual peaks matched. Right? So you take those. I will put the answer key for the practice problems online tomorrow. And then the other ones you'll bring back next week. And we'll finish up spectroscopy.
This is 340.